given that it starts off in state, the controller starts off in state closed, and then it gets this sequence in time of these input signals, you should be able to deduce by looking at the state transition table, these rules, a table of rules for deciding what the next state should be. You should be able to deduce the sequence of states. Okay? Starts off with this one. This is a sequence of input signals, and therefore the states, there'll be a sequence in time, a sequence of states as it switches back and forth, open, closed, depending on the sequence of input signals. Right? So as a bit of homework, you could try this. What we have here now is a list, a sequence of the state. What is the state of the controller at a given moment in time? Okay? So it starts off at closed, and then it opens, and then it stays open, and closes again, and then opens, stays open, then closes, stays closed, and stays closed. Okay? Given this input sequence, or this sequence of input signals, do for homework, deduce, given the transition rules we talked about here, deduce that this should be the sequence of the state of the controller over time. Okay? Now, we haven't yet really defined, and that will be in fact the next board, a formal mathematical definition of what a finite automaton is. We're just, these few sessions are more introductory, giving you a feel for what an automaton, finite automaton is before we do the formal definition. Because if you start with the formal definition first, it won't mean anything to you. It'll just be a bunch of symbols and you won't be able to relate to it. So for didactic, purposes of education, for didactic reasons, we are doing this sort of overview first, and then later we will give a formal mathematical definition of a finite automaton. Right? Now, but you have a sort of vague idea now of what an automaton is. So we're going to translate this automatic door controller, this door controller, into the terminology and labels of a finite automaton. So you're now starting to get a feel for what an automaton is in terms of its formal definition. So what we'll do next, you'll see, next board actually, a couple of sessions from now, you'll see that this feeds in, it becomes a part of the mathematical formal definition of an automaton. Right? So a finite state machine, the door controller is a good example of a finite automaton. Because you can represent this door controller as a finite state machine or finite automaton, same thing. Right? Now this will become clearer later. It might pay you to come back to this after you understand the formal mathematical definition of a finite automaton. But this is giving you a sort of foretaste. Okay, so here you have what's called a state diagram, or if you like, a state transition diagram, and this is a sort of typical way to represent an automaton, a finite automaton. In other words, there'll be some states. Right? In this case, for the door controller, we only have two states, closed and open, and there will be input signals, if you like. That's what these arrows correspond to. Okay, and the state transition, from current state to next state. Well, the arrows and the state together represent that. For example, so this state diagram or state transition diagram is a kind of summary a nice compact visual summary of all those transition rules, list of states, and the input signals, right? But now, one of the reasons it's a state diagram, obviously it's a diagram, and it's a state diagram because it lists the states. You see the states here. Often, a state diagram is sort of short for state transition diagram. Now, transitions, like when it transitions from one state to the other, under what circumstances? Well, it depends on the input signal. So let's do a few. So give you a feel for the nature of a state diagram. Say the controller is in state closed, right? So the door's closed, and then it gets an input signal front. Well, the door should open, right? So this arrow here, this arrow is called a transition, a switching, if you like. So these arrows, they're all transitions. That's the technical word used in a state diagram or state transition diagram. These arrows are they're called transitions. Now this so an input signal front comes in. You're currently in the state closed. And imagine you are the controller, and so you'll have a rule. That'll be in the state transition table, and that rule will tell you switch to the state open. So this state diagram, tells you, given your two factors, your current state and the input signal, what is your next state? Well, you follow the arrow, you follow the transition, and you move to open. Now say you're in state open, and an input signal front comes in. Well, the next state will be still opened. In other words, don't do anything. Just stay in your current state open, right? Or if you're in state open and an input signal rear comes in, well, again, don't do anything. Just stay in state open. And if you're in state open and an input signal both comes in, again, just stay where you are. So if you're in state open and either of these three input signals comes in, stay in state open. Now if you're in state open and the neither signal comes in, so nobody's on the plates, on the pads, well then you should shut the door, right? Conserve energy. So when the input signal's neither, then you switch, you transition from this current state to this one. So, okay. Now if you're in the closed state and the input signal is either one of these three, rear, both, or neither, then you stay closed. Okay? So this diagram, in a rather compact way, summarizes everything, right? You've got the states, you've got the possible input signals, and you've got the rules of transition, because you can deduce those rules just by looking at the state diagram, the state transition diagram. Like, for example, if current state closed and input signal is front, then next state equals open. Right? That's an example of a transition rule. And you could make, well, how many rules could you make? We've got three here, like if closed and rear, then closed. If closed and both, then closed. So you've got three rules here, 4, 5, 6, 7, 8. You've got 8 rules in that state transition diagram, implicit. Right? Now, another remark, that's why I hesitated just a bit before. Have a look at this. Does it remind you of something? Have you seen that kind of thing before? In the previous chapter? I'll give you a strong hint. What does it look like? It's a graph, right? It's a graph. I mean, we don't have little dots or small circles. I mean, these circles now are quite large. That's because we've labelled them. I need enough space to put the labeling word, the label, inside the node. Right? So we have 2 nodes here, and these arrows now, what are they? Well, they're edges. Right? They're edges. So this state diagram, or state transition diagram, you can look on as a graph. Right? It's a graph. It's a labelled graph, because both the states and the edges are labelled. Right? So it's a fully labelled graph, and it is a directed graph, right? Because the edges have arrows. It's all arrowed. So another way of looking at a state diagram or a state transition diagram is that it's a directed, labelled graph. Okay? So the nodes correspond to states. Here are two nodes, two states, and the edges, or these transitions, if you like, the transitions correspond to edges. Okay? And the transitions, well, they're dependent on the input signals. So in a sense you could say the edges correspond to the input signals as well. Okay? So that you can probably understand now more why Sipser talked quite a bit about graphs in the introductory chapter, chapter 0, because now that we're doing the actual theory of computation, this notion of a state diagram is critical. It's like basic to the theory of computation. So to understand what a state diagram is in mathematical terms, and we'll come on to that increasingly when we get a formal mathematical definition of a finite automaton, or finite automata, the plural form, then the state diagram is critical. And what is a state diagram? It's a graph, right? So you need to understand basic graph theory, and we did it in fairly elementary form. And if you're a specialist in graph theory, the graphs that are used in this whole course, pretty simple concepts, but very useful, right? Very powerful mathematical techniques. Okay, so a state diagram is a graph. Right? Now, next session, I will, the 1, 2, 3, 4, 5, 6, 7, 8. There are 8 transition rules, implicit, not explicitly stated, but they're implicit. They are deducible from this state diagram or state transition diagram. Now, so at the beginning of next session, I will show you a state transition table, and that table lists all 8 transition rules, rules of the form. If current state is such and such, and input signal is such and such, then next state is such and such. Right? It lists all 8 transition rules. It's a state transition table. Okay? And I'll stop it.